Hi, folks. Here we have a block of iron and a block of gold in contact with each other. The iron is cold, the gold is hot, and the iron and the gold are the same mass. When they're in contact with each other, of course, the gold is going to cool off because of the iron, and the iron is going to warm up because of the gold. Both of those statements indicate that heat is moving from the hot thing to the cold thing. That's what happens in the world. If you put something hot on something cold, heat is going to move from the hot thing to the cold thing. That's how the world works. So that is called thermal equilibrium. They're going to arrive, and the heat is going to continue to move until they're both the same temperature. That's thermal equilibrium. It's just like if you put a cold glass of soda on the table in a warm room. The temperature of the soda is going to drop by heat from the room coming into the soda until the soda is the same temperature as the room. That's how the world works. So now, our task in this problem is actually going to be to guess where that temperature is going to be, where that final temperature is going to be. Is it going to be exactly in between the cold and the hot temperatures? Or is it going to be closer to the hot? Or is it going to be closer to the cold? Since the metal blocks here are of the same mass, the only way to figure this out is by looking at the other available difference between these metals, which would be the specific heat capacity, C. The specific heat capacity is the quantity that you used in the web assigns for the Q equals M times C delta T problems. But the meaning of this in English is the amount of energy it takes to raise 1 gram of the substance by 1 degree Celsius. So it takes a lot more energy to raise 1 gram of iron by 1 degree Celsius than to raise 1 gram of gold by 1 degree Celsius. In fact, it takes almost 4 times more energy to raise iron than to raise gold by 1 degree Celsius. So what does that mean? That means that iron here is the heavyweight in terms of energy. So if iron is the heavyweight in terms of energy, then the final temperature is going to be closer to the temperature of the iron. So the final temperature is going to be colder than the exact midpoint. It's going to be closer to the cold temperature than the hot temperature. That is not easy to understand. I mean, for some of you that might seem like common sense, but for others of you, and me included, that is not quite as easy as common sense. So let's look at what's behind this at the molecular level. So we have the same amount of mass here. It's some number of grams, but let's see. Let's say this is a gram of iron. Let's say this is a gram of gold. And gold, I think, is denser than iron. So every gram here requires 4 times more energy to raise the temperature by 1 degree Celsius than every gram of gold. Okay, so that means energy leaves gold very easily, but the iron just absorbs that without raising its temperature very easily. Does that make sense? So if I lose 1 joule of heat from the gold, let's say it's 1 joule of heat from the gold, that's going to drop the temperature of the gold by a lot. All right. But that same 1 joule of heat is just going to get absorbed by the iron, and it's going to raise the temperature of the iron only a little. Does that make sense? This is the meaning of the specific heat capacity. So because the specific heat capacity of gold is so low compared to iron, the temperature of the gold changes drastically for every joule of heat that moves, but the temperature of the iron only changes a very small amount. In fact, 4 times less than the temperature of the gold changed. So that means that as heat moves from the gold to the iron, the gold temperature this hot temperature, it's going to go down a lot. but the cold temperature, the iron, is only going to go up a little bit. Eventually, they have to end up at the same temperature. That's how the world works. Hot things cool off, cool things warm up until everything is the same temperature. So that same temperature is going to necessarily end up being closer to the cold. Why? Because every time heat moves, the cold temperature raises only a little, but the hot temperature drops by a lot. Now, it's important that you understand that this is not because the hot temperature will always drop by a lot and the cold temperature will always raise by a little. It is because the specific heat capacities, all right? In this problem, if it were the case that the iron were hot and the gold were cold, the specific heat capacity of the iron is still higher than gold, so the iron will be, the temperature of the iron will drop by a little, and the temperature of the gold will go up by a lot. So your answer will be that the final temperature is closer to the cold temperature, the gold's temperature. Okay. So I'm trying to say that the important concept here is that the specific heat capacity is going to control how effectively a material can absorb or give off heat. It's the specific heat capacity. It's the higher specific heat capacity is going to allow that's going to allow a material to change its temperature less, and it's a lower specific heat capacity that's going to allow a material to change its temperature more for any movement of heat. Okay, that's number 3.